discussing three-phase induction motor equivalent circuit, how to represent it in the form of electrical components. The topics to be covered will be stator equivalent circuit, the rotor equivalent circuit of the induction motor in totality, phasor diagram of the induction motor, the Thevenin's equivalent circuit of the induction motor, and the power distribution in three-phase induction motor with respect to the equivalent circuit. So first we will start with the stator equivalent circuit. You can see the circuit of the stator, that is the R1 is the stator resistance, X1 is the stator winding reactance. These are all per phase quantities. Your RC is the core loss resistance, IC is the core loss component of the no load current, XM is the magnetizing reactance, IM is the magnetizing component of the no load current, and I0 is the no load current, which is the vector sum of the core loss component current and the magnetizing component current. The current drawn by the stator is given as I1 and the voltage applied to the stator is V1. So the equation becomes as V1 is equal to V1 dash plus I1 into R1 plus JX1, that is the impedance drop in the stator windings. But this V1 dash is equal to the minus E1 because V1 dash is the voltage after the drops, what we get it at the before entering the air gap, what is the voltage available there, that is known as the V1 dash. But V1 dash will be just in opposition to the induced EMF, because induced EMF will be opposing the very cause which is producing it, and that is the supply voltage. Hence they are just in opposition, the supply voltage and the induced EMF. The no load current is the phasor sum of the core loss component current and the magnetizing current. Now this will be similar to the primary side of the transformer. The I0, the no load current function is to create the resultant air gap flux in the induction motor, and it also supplies no load losses. That no load losses includes the core loss, the mechanical losses, that is friction and windage losses, and the stator and the rotor copper loss. As we know, the no load current is consisting of the core loss component current and magnetizing current. So the core loss component current is nothing but V1 dash divided by the core loss resistance RC, and the magnetizing current will be equal to V1 dash divided by the magnetizing reactance. Now we will discuss about the rotor equivalent circuit. The rotor equivalent circuit we had discussed before also, because when the motor is running at any speed, the induced EMF is equal to slip into the secondary induced EMF at standstill, and S is the slip of the given circuit depending on the rotation of the rotor. Now over here the frequency is slip frequency, and therefore the rotor current is defined as I2 is equal to SE2 by Z2, that is the impedance of the rotor circuit. So the equation becomes as SE2 divided by R2 plus JSX2. Now this whole equation can be divided by the slip, and the equation becomes as E2 by R2 by S plus JX2. Now this denominator can be represented in the electrical circuit as the reactance is X2, resistance is a variable component, that is R2 by S, which depends on the slip of the given rotor. So over here the frequency in the given circuit will be F, while actually the frequency in the rotor circuit is the slip frequency, and that is dependent on the rotation of the rotor. But when we define it electrically, then we take this induced EMF as E2, the reactance as X2, and the resistance changes to R2 by S. In that case it is corresponding to the input frequency as the same as the supply frequency. So when we try to have the equivalent circuit, now the equivalent circuit E2 will be the transformation ratio voltage from the supply voltage. Depending on the transformation ratio, you can calculate the E2, and you can say that as per the induced EMF what will be the E2 as the transformation ratio that we have done before. That is your E1 by E2 is equal to N1 dash by N2 dash, which is the effective turns ratio. Now the transformation ratio, when you want to take this secondary side or the rotor side circuit referred to the primary side. So when you refer to the primary side, in that case the transformation ratio has to be taken into care of, and that is E1 by E2 is equal to N1 dash by N2 dash, effective number of turns ratio, is equal to I2 by I1 is equal to A, same as the transformer. Only difference is that there we have got the coils number of turns ratio N1 by N2, while because over here the coils are distributed in the circumference and we have to take the winding factor into account, hence the effective turns ratio comes into picture, and that is N1 dash by N2 dash. So the resistance of the rotor has to be referred to the stator side, that will be equal to N1 dash by N2 dash whole square into R2, and when we refer the reactance from the rotor to the stator side, that becomes as the N1 by N2 dash whole square X2, that is equal to A square X2. So the circuit over here is the equivalent rotor circuit referred to the stator side. Now because all this circuit, when we are referring to the stator, it is at the same frequency F, supply frequency, so the stator and the rotor circuit can be combined. A total equivalent circuit of the induction motor comes as your stator resistance and reactance, then the magnetizing component and the core loss component, and finally the rotor circuit referred to the stator side, that will be X2 dash and the R2 dash by S. Now the R2 dash by S can be rewritten as R2 dash plus R2 1 minus S by S, that we have done before. So same thing has been represented over here on the rotor side, and this is also referred to the stator side only. So now after this we know the equivalent circuit, the stator and the rotor circuit combined. We'll try to draw the phasor diagram of the induction motor. Now when we draw the phasor diagram of the induction motor, as in transformer we take for the different loads, induction motor we take at two conditions. One is at the standstill, the other one will be at any rotor. So one will be at the motor when it is running with the load or it is running at any slip almost near to the synchronous speed, that is on load the slip is almost 2 to 5%, and at standstill where the rotor will start rotating, we have given the supply, that momentary function will be taken as the standstill portion of the phasor diagram, and because the two is different, so we'll discuss one by one. Whatever phasor diagram we draw, because the flux is the linking quantity between the stator and the rotor, so the flux is taken as the reference. Then we take the induced EMF. The induced EMF will be lagging the flux by 90 degrees. Then you will have V1 dash, which will be equal to minus E1. Then the secondary induced EMF E2, which will be derived as per the turns ratio. We have got the no load current. The no load current will be divided into two parts, and the theta 0 or cos theta 0 is the no load power factor. Then we have got the magnetizing component of the no load current, the core loss component of the no load current, and then we'll see that what is the secondary current or the rotor current drawn by the rotor at no load. Now at no load the reactance is very high because slip is equal to 1, so the reactance is X2, that which is 2 pi FL2, and because F is the supply frequency, hence the reactance of the rotor is quite large, hence you have got a large angle theta 2 over here, and therefore the no load power factor is much more higher at standstill. Then this is the drop on the rotor side, resistive drop, the reactive drop, and then just opposite to I2 we take the I1 dash, similar to the transformer. Depending on the turns ratio, I1 dash can be calculated with respect to the secondary current, that is rotor current, that is I2. Then find the phasor of the I0 and I1 dash, and you will get the resultant current I1, that is the stator current. Add the stator currents to the V1 dash voltage or minus E1, and that will give you the exact supply voltage V1. So the stator drops, resistive and the reactive drop has been added to the V1 dash, and you get the supply voltage V1. So now if you see, the no load power factor is very poor due to the high rotor reactance. It is due to the high rotor reactance that the power factor is very poor under the standstill condition. Now once the rotor starts rotating, it will achieve a steady state condition somewhere just below the synchronous speed. So we'll draw the phasor diagram under the load condition. So the phasor diagram of induction motor at any slip S. Again we'll start with the flux, then the induced EMF on the primary and the secondary side, the primary V1 dash voltage which will be just opposite to the induced EMF on the stator side, then the no load current, no load power factor, cos inverse theta 0, magnetizing current, the core loss current, the load current. Now you can see the rotor current as the angle between the rotor current theta 2 is much less as compared to the theta 2 at standstill. That is, when the rotor starts rotating, the frequency of the induced EMF on the rotor side reduces, hence the reactance of the rotor also reduces and the theta 2 angle reduces to a significant amount. Now this is your resistive drop on the rotor side, add the reactive drop, and then you can find out the I1 dash that depends on the effective turns ratio of the induction motor. So I1 dash will be in proportion to I2 and the transformation ratio. Then find out the total stator current, that is equal to I1. Now once we find out the I1, we'll try to find out the supply voltage. So we'll add stator drop and resistance drop and the reactance drop, and finally draw the supply voltage V1. So when you draw the phasor diagram of the induction motor, we go from the right side of the equivalent circuit and come to the left side, while actually the power diagram is coming from the left side. The supply voltage, it is coming to the rotor side, but when we draw the phasor diagram, we take it in opposite, that is, we go from the right side to the left side, just similar to the transformer. It's very similar. Only thing is that you have to take care of the secondary current angle, that is theta 2 has to be greater in case of the standstill condition and theta 2 will be very small in case of the motor running at any slip. Now over here, if you see, one more major difference with the transformer is we have not taken the voltage drop because rotor conductors are short circuited. So V2 is equal to 0. We don't have the secondary voltage because the rotor conductors are short circuited. Hence your V2, the terminal voltage, is equal to 0. So your induced EMF is only dependent on the drops in the rotor, and therefore the E2 quantity is quite less. Now this is the angle between your primary current and the primary voltage, that is theta 1. So that can give you the actual primary stator side power factor. Now come to the Thevenin's equivalent circuit of the induction motor. So when we try to calculate the Thevenin's equivalent circuit of the induction motor, we have neglected the core loss component over here, because core loss component, it is connected in parallel to the circuit and by R1 into jx1 plus xm, that is the equivalent impedance of the circuit, into the reactance xm, that is the voltage across the xm will be the Thevenin's voltage. What is the equivalent resistance? Thevenin's resistance or Z equivalent resistance will be R1 plus jx1 into xm, that is the parallel combination of the resistance R1 jx1 plus the xm. So when you find out the parallel combination, it comes to as solution of this, and that will come as VE becomes as V1 xm by x1 plus xm, and equivalent impedance becomes as equivalent resistance and equivalent reactance. Equivalent resistance will be equal to R1 xm divided by x1 plus xm, and equivalent reactance will be x1 xm divided by x1 plus xm. Every time we have got a complex number, we multiply its conjugate and we try to differentiate the real part and the imaginary part. The real part represents the equivalent resistance and the imaginary part represents the equivalent reactance. So that is how we have segregated the RE and XE. Now the Thevenin's equivalent circuit of the induction motor. What finally we get the equivalent circuit is, exact equivalent circuit is, RE is the equivalent resistance for the stator and the magnetizing component. XE is the equivalent reactance for the stator side reactance and the magnetizing reactance, and the rotor circuit is added to the circuit. So your rotor current becomes as VE divided by the impedance of the total circuit. So the total torque will be given as M by omega S, that is I2 square R2 by S is the torque into M by omega S. So M is the number of phases in the given circuit. Because we are discussing the three-phase induction motor, so M will be equal to 3. Omega S is the synchronous speed of the motor in radians per second, that is your 2 pi ns VE square by the impedance square of the given circuit into R2 by S. Now, as per the equivalent circuit, we have done the power distribution or the power flow of the power flow in the induction motor. Over here from V1 the stator input is given. After stator input is given, the first comes the resistance of the stator, where the stator I square R loss will take place. Then between the leakage reactance and the magnetizing reactance, the stator core loss takes place. Then the current goes to the rotor side, there is the rotor loss, and finally it is the mechanical power developed in the rotor which is given as electrical load R2 1 minus S by S. So this is the power flow diagram as per the induction motor equivalent circuit. This is your after this magnetizing reactance or the core representation, the rotor input power, that is the power transfer to the air gap, is given. So today we have discussed the stator and rotor equivalent circuit, the complete equivalent circuit of the induction motor, the phasor diagram, Thevenin's equivalent circuit of the induction motor, and the power distribution or the power flow in the three-phase induction motor with respect to equivalent circuit. Thank you.